Okay, so let's look at this problem. We want to look and construct the shear force and bending moment diagram for this. Like all these problems, the first step is going to find the reactions, because the reactions will give us, in this case, they'll give us our shear values to start and stop with. And because they're pins, we'll already know something about the moment. So over here, I'm going to assume that I have a force in the X and Y direction. And then over here at B, I'll assume that By is up. So let's find these reactions. So first I'll just some moments about A. You could do B at B also. We'll just do A to start with. So I'm going to sum moments about A and use right-hand rule. So about A, I have a force, an applied moment, and a reaction. So what's the moment about A of this applied 600-pound force? Will it create positive or negative moment? Negative. So I'll have 600-pound force, and its moment arm is 10 feet. I've got this applied moment. Is it positive or negative? Also negative. And that's 4,000 pound-feet. And then I'll have my reaction By, and what kind of moment is it creating about A? Positive or negative? Positive. And it has a moment arm of 20. So what is By equal to? Who's got a calculator? It looks like it's going to be, let's see, that's 6,000, 10,000. What's 10,000 divided by 20? 500? Is that right? Is it positive? Yeah. Anybody get that? And then we'll quickly sum forces in the Y direction. Make sure we're in equilibrium. I'm assuming up is positive, so I have AY acting up plus BY acting up, and then I have my 600-pound force acting down. So it looks like AY is going to be 100. So we found the reactions. Any questions about that? Okay, so this is what I like to do. I like to go ahead and construct like a template. There's my limits of my problem from left to right. And then I'll come in here and define a positive x-axis, positive axis for my shear, and tell you all my shear values will have units of pounds. I also know that as I go from left to right underneath this 600-pound force, something probably will change. And also I've got this applied moment. Probably something on my moment diagram will change there. So I'll add that as kind of lines where I expect something to change on my diagram. So again, we're going to work from left to right. So starting on the left-hand side, what's AY? It's 100. Is that positive shear or negative shear? Positive. So we're going to start off at 100. When I get all the way over here to BY is 500 pounds. Is that positive or negative shear? That's going to be negative shear. Okay, so I have my starting point, my ending point. I know that in between, that the change in shear between any 2 points is the area under the load diagram. And, that the slope of my shear diagram is equal to the load. So with those two things, let's see if we can construct this. I know something's going to happen here at 10 feet when I go from left to right. I know the change in shear is going to be equal to that 600-pound force. So let's look at what's happening between 0 and 10. Well, according to our relationship, the change in shear is the area under the load curve, and the area under the load curve is Nothing, 0. So that means I should have no change. So I should land here, and I should still be 100. And the slope of that curve is going to be equal to the load, and the load is 0, so I'll connect those 2 points with a line of 0 slope. So you can see in this first segment, 10-foot segment, the shear is constant and equal to 100. Now, as I go from left to right and go under this point load, what happens to my shear? It changes by 600 pounds, and that force is down, so it should drop to minus 500. Now the change in shear between these 2 points, which you can see my target value is also 500, which means what's my change in shear? 0. Was it backed up by my relationship? It says the change in shear is the area in the load diagram. Look at the load, the force. There is no force, so there is no change. So that matches. It says that the curve connecting these two, the slope of that curve is equal to the load. Well, the load is 0. That means that curve has a 0 slope. And there it is. So there's my shear diagram, my shear force diagram. Questions about that? Okay. So let's draw our moment. So I'll assume a positive axis for my moment and say these will have units of pound-feet. Do I know my moment anywhere in the structure? What's the moment of a pin, an external pin? 0. What about on this side? Same thing. So I know where I'm starting. I know where I'm going to end. I also know that the change in moment between any 2 points is the area under the shear diagram, and that the slope of my moment diagram is given by the value of shear. So here's a nice segment where I can see my shear force is continuous. So what is the area under the shear diagram? Looks like it's 100 times 10, so that's 1,000, and it's positive. So if I start at 0, I should end up at 1,000. And what's the shape of that curve? Yeah, it's given by the shear, and the shear is constant, positive. So I have a constant, positive slope. And I'll just mention on there that would be 100 to 1 slope. Okay? Now what's next? Well, let's go back up here and remind ourselves that I've got this point moment. What's going to happen here when I go from the left side to the right side of that on my moment diagram? That's a clockwise moment, so that's going to be a positive jump up. So whatever I get right here, as I go from the left to the right, it's going to jump up 4,000. So let's just look at the change in the moment for just, I'll kind of double hatch this section right here. Let's just consider this section of the shear diagram over the next 5 feet. So the area into that part of the curve is going to be minus 500 times 5. So what's that? 2,500? And it's negative. So I'm going to go from 1,000 to negative 1,500. Everybody see that? And the slope of that curve is given by the shear. And what's the shear in that range? Constant and negative. So there's a negative constant slope. In fact, if I looked at that slope, you would see it would be minus 500 to 1. And we could find a point where there's actually no moment in the beam. It's going from positive moment to negative moment. Now what happens as I go from left to right, I'm going to see a jump in my moment of 4,000. So if I'm at minus 1,500 and I jump to 4,000, that should bring me up to 2,500, right? And now the change in moment over the last 5 feet should be the area under the shear diagram, which is 5 times minus 500 is negative 2,500. That brings it back to 0. And the shape of that curve is given by the shear, and the shear is still constant and negative. And that part of the curve would also be a slope of minus 500 to 1. Any questions about that one? I wanted to give you one that had a point, that had an applied moment in it. Mr. Preston.
I'm not really sure. Why is that moment positive?
Which moment positive?
The 4,000.
Well, the rule is if it's a clockwise moment, it creates positive change in your moment diagram.
No, it doesn't matter where it is on the beam.
No, it's applied right there. That's why you see that your moment jumps. As you go from the left side to the right side, there's a change in moment of exactly 4,000.
Yeah, but as long as it's clockwise, though, it's going to be positive.
Right, if it's counterclockwise, it'd be a negative change. So the direction is important.
That's only for bending moment, correct?
It's only for... Okay, my question to you would be, what other moment would it make an effect on?
Well, when you have, I think what his question was, when you sum your moments, you assume the counterclockwise would be positive.
Okay, so we're back to our original discussion that the sign convention for statics and the sign conventions for shear force and bending moment can be different.
Right. I think that's where the mix-up was. Yeah. You had that going one way and that going back.
So wouldn't that bend the beam into a frown shape, I guess?
Well, let's see the way it would bend the beam. We can see that positive moment makes it smile, negative moment tries to make it frown, and then it goes back to positive moment. So this is going to be a very strange looking beam. So it would be something like, let's see if I can guess where this would happen. Also at 0 moment, that's what? It's like an inflection point, right? So what I would have would be, let's see if I could do this. So I know I have some positive bending here, and then I would have some negative bending, and then back to positive bending. I don't know how I can draw this. It's going to be really weird over here. This is going to be, this is going to be kind of S-shaped. So it's going to look something, this is exaggerated like that. So that moment is causing the middle of that beam to want to twist clockwise. And you can see it trying to deflect that way. See that? So that side would be positive moment, that side would be negative moment. And then this would be the point where it would go from negative curvature to positive curvature. Positive to negative. And it's got this abrupt change here because of the applied moment. So that would be my guess at what the shape might look like. It's probably going to, I don't know what the scale would be. It would depend on the forces. If that bothers you, this is one of those things where you just memorize it. Clockwise moment creates positive change. And if you remember that, well, then the opposite is true. If it's not clockwise, it must create negative change. It's the same. This one, I think, is easier for you to understand. If you have a negative force, it creates a negative change in your shear diagram. That one may be more intuitive. This one, not so much.
On the problem statement, in a different problem, would they have that? was negative, would they write negative 4,000 foot-pounds?
No, the direction is given by the arrow. Just like the force. The force is down. You just have to remember that what our shear force definition is, and that would cause a negative change in shear.